everybody. Today we're going to begin looking at section 2 of chapter 3, and in fact we're going to be talking about Newton's laws of motion. Now if you'll remember from section 1, Newton also came up with the universal law of gravitation. Now we're not going to talk about that here. These three laws are a little different. So we're going to take them a day at a time, too. We're not going to do all of the notes today. We're going to do part today, part Wednesday, and another part next week so that you get a very good understanding of how these laws work, because they are the cornerstone of physical science as we know it, physics and chemistry and physical science. So these are obviously very, very important. Now, the main idea of section 2 is that Newton's laws of motion relate the change, and notice I'm going to all cap the word change. They relate the change in an object's motion with the forces acting on it. Okay, I'll give you a moment to get that down. Newton's laws of motion relate the change in an object's motion. Okay, so remember, forces cause changes in motion. Okay, now let's talk for just a minute about Sir Isaac Newton. He was a genius, the genius of his time, sort of like Albert Einstein was the genius of the turn of the 19th to 20th century, and Stephen Hawking is the genius of the 20th to 21st century. So Isaac Newton was just as brilliant as they are. He was just way ahead of his time. And because of him, we have a lot of the things that we use today because of his laws of motion. Now, he lived in the 1600s, and in the mid to late 1600s, he wrote a book called the Principia, and in the Principia, he explained the three laws that he formulated. These laws govern motion and the forces causing the motion. Today, we're going to look at Newton's first law of motion. Okay? Newton's first law of motion. Now, basically, this law says that an object that is at rest or an object that has constant velocity, either one, it will maintain that rest state or it will maintain the constant velocity as long as, so there is a requirement, isn't there? As long as the net force acting on it is 0. Okay? Now remember, the word net means to sum or add all the forces together. Net means sum. Okay? So if you look at the net force, if it has a value of 0, this simply means there's nothing left to change the motion. So the object continues to do what it's doing, stay at rest or stay at constant velocity. Now, if you add the forces up and the sum is not 0, then the object will change motion. If it's at rest, it will start moving. If it was moving at constant velocity, it will either slow down or speed up. The motion will change. Now, what we're looking at today is what happens when the net force is 0. I like to say that when the net force is 0, all the forces balance out mathematically. Now, that doesn't mean that if one cancels the other out mathematically, that the forces no longer exist. That's not what I'm talking about. I'm talking about if there are forces acting on an object and two point in the opposite direction and have the same numerical size, then they will balance out mathematically. Let's take a look. Look at this first object. This object has a force of 3 newtons pulling up and a force of 3 newtons pulling down. Now, they're opposite directions and they have the same size, 3 newtons each. So when you add them, one in the positive and one in the negative direction, you get 3 minus 3. That's 0. They cancel out. Now look at the other two forces. There is a force of 3 newtons pulling to the left and a force of 6 newtons pulling to the right. Well, 6 newtons minus 3 newtons the other way does not equal 0. In fact, it equals 3 newtons, I'm sure you can see. So that means the net force is not 0. The forces don't all balance out. So the object will change motion. It will not stay at rest. It will not stay at constant velocity. It will change motion. Look at the next one. Here we have 3 newtons pulling out the back and 3 newtons pulling out the front, opposite directions, and they have the same magnitude. So guess what? They cancel out. And if you'll look, there are no other forces acting on this object. So here, the net force equals 0. It is 0. So the object will stay at rest, if it's already at rest, or stay at constant velocity, if it's already at constant velocity. Whatever it was doing initially, it will continue doing that because there's nothing to change the motion because the forces balance out. Okay, look at the next one. Let's see what's going to happen here. Here we have 3 newtons pulling up and 3 newtons pulling down. Opposite directions, same signs. So if you say 3 minus 3 newtons, you're going to get 0. Oh, but look, there is one more force acting on our object, and there's nothing to balance it. So this becomes the net force, okay? And because it's not 0, then the object will change motion because there's something left to do that, okay? Let's take a look at the last example. Here we have an object with 3 newtons pulling out the back and 3 out the front. Opposite directions, same size, they cancel out. Here we have 6 newtons pulling out the top, 6 newtons pulling down the bottom. Same size, opposite directions, they're going to balance out. And guess what? The net force, therefore, is 0. So the object will either stay at rest, if it's already at rest, or constant velocity, if it's already at constant velocity. There's nothing left to change the motion, okay? So if the net force is 0, if the forces all balance out, the object will continue to stay at rest or stay at constant velocity. Now, why will it do this just because there's no net force? Well, you see, all objects, in fact, anything made of matter, has a property called inertia. Oh, there goes my clock. Hang on just a minute. Let's let it get over with. Okay, there we go. So, inertia is the property of all matter that resists change in motion. That's very important. You have inertia, so your body resists change in motion, okay? If any of you have ever been up north where there are big hills, if you've ever run down a big hill, you know exactly what I'm talking about. If you're running down a big hill, can you suddenly stop in an instant when you get to the bottom? No, because your inertia wants you to keep going forward in the same direction at the same speed. If you want to stop, you have to slow down to stop. if you're running along a road and you want to go left, you can't suddenly be going one direction or forward and then suddenly turn left and make a sharp turn. It's just not possible unless all you're doing is walking. If you're running, it's extremely difficult to do that, if possible at all, because your inertia doesn't want you to change direction either. Okay? In fact, inertia, being a property of matter, gets bigger with more mass. So bigger objects have more inertia or more resistance. That's why it takes so much more force to accelerate a tractor-trailer truck than it would a VW Bug, because the tractor-trailer truck has more mass, it has more inertia, and you need more force to change its motion. Look at these examples here. This cart is at rest, and its inertia wants it to stay at rest. Now, if you push the cart, you can overcome its inertia and accelerate it. But you do have to do that. You can't just stand there and expect the cart to suddenly start moving on its own. It requires an external force, like one from you, to start it moving, to overcome its inertia, to overcome the resistance to change in motion. Otherwise, the cart would stay at rest. Okay? Now, what about objects that are moving? So this object was at rest. Now this object, it's a box, a red box sitting on top of the car. It's already moving. And the car strikes a barrier and stops. But the box, not being fastened to the car, wants to continue moving forward. So the stopping force was not being applied to the car since it wasn't tied down. And because there's no force to overcome its inertia, the box continues forward at the same speed, because that's what its inertia wants it to do. And if you'll think about it, that's exactly why we wear seat belts, isn't it? We wear seat belts to transfer the braking force of a car to us so that our inertia is overcome and we decelerate along with the car instead of, well, going through the windshield, which would not be fun. All right, look at this little picture here. Here you have a little toy car with a little driver in it, and it's moving at a constant 10 meters per second. Now, how can that be? You see, the little toy engine applies 10 newtons to move the car forward, but there's air resistance and friction between the tires and the ground that are resisting that, okay? So here, the net force is going to be 10 minus 10, or 0. There's nothing left to overcome the inertia of the little car, so therefore it wants to stay moving forward at 10 meters per second. It doesn't want to change the 10 meters per second because there's nothing there to change it. So inertia keeps it moving forward. Okay? All right. So today, what is our takeaway from this? Well, our takeaway basically is, as long as the forces acting on an object balance out, as long as the forces balance out, the net force is 0, and the object will stay at rest, at rest, or constant velocity, because there's nothing to overcome, C-O-M-E, overcome inertia. Okay? You've got to have a net force to overcome inertia and change motion. If there's no net force, there's no overcoming the inertia. The object maintains what it's doing initially, either at rest or constant velocity. All right, that's what we're going to do today. That's what we've done, and we're finished with that. Tomorrow, or if you want to start on it now, you can. If you go into tomorrow's folder, you will find discussion number 10, which is on Newton's first law. I've got some really cool videos. Guys, you are really going to be happy because one of the videos is going to show you how they use Newton's first law of motion in NFL football. Oh yes, football. And it's only a few minutes long, but it's very informative, so I think you'll like it. All right, guys, I will see you again on Wednesday when we will cover the second part of the notes. All right, so have a good day. See you soon. Bye.